In this lecture, we learn about RS codes. RS codes are the non-binary cyclic codes. Previously, we have learned about the binary cyclic codes. In non-binary cyclic codes, we consider K symbols coded with N symbols, and the length of each symbol is of M bit. So 2k possible symbols are in fact is 2km, and they are represented by a symbol set of 2 raised to power n m symbols. So the advantage of doing this is that we are increasing the distance property of the code. For example, if the value of k is 4 and the value of n is 7, then we have a 7 4 cyclic codes. So here we take the value of m is equal to 3. So the total number of possible combinations we take from this is 2 raised to power 12. So we are using 2 raised to power 12 combinations from 2 raised to power 21 combinations. So it is a very small fraction. Uh, Actually, the fraction of 1 raised to power 2 raised to power 12 is used from this symbol set. So if we increase the value of m, so in fact we are increasing the distance among the symbols, because we are increasing the distance property and decreasing the fraction of symbols used from this large symbol set 2 raised to power n. So the condition for this is that k will be less than n, and n should be less than 2m plus 2. Or we can say that the difference between n minus k, that is equal to 2t. And we learn in the linear codes that t is the error correcting capability of the code. So we have 2 times more symbols in n to correct the symbol errors. T symbols are used to detect the errors, and T symbols are used to correct the errors. So the value of nk is n value is 2m minus 1, and the k value is 2t less than the n coded symbols. So the minimum distance is in fact is n minus k plus 1. So the minimum distance is in fact is n minus k plus 1, because n minus k is equal to 2t. N minus k is equal to 2t. And here if you know from linear block codes that t is equal to d min minus 1 by 2. So this relationship holds. So the erasure correction capability of the code is rho is equal to d minus 1, and that is equal to n minus k. So we can say that the error correction capability of the code is 2 alpha plus gamma, where alpha is the number of error patterns to be corrected and gamma is the erasure correction, and that is less than d min, and d min is less than n minus k. So RS codes are a very good property to correct uh, a burst of errors. So if a 25-bit burst of errors will occur, so it will able to correct it if the value of t is 4. So value of t is 4 means that it is able to correct 4 symbol errors, and the n minus k code is 2t, which is in fact 8 uh, symbols uh, less in k than in n. So n minus k 255 minus 247 is 8. So there is a difference of 8 symbols. So we can correct half of the symbol errors. So it is possible to correct with the help of RS codes when we have the burst of errors. To learn the RS codes, first we know the property of Galileo's field. Galileo's field is in fact is a field which is finite and comprise of any prime number p, and it has p number of elements. And if we want to extend this field, so we have p raised to power m symbols in this Galileo's field, and m must be a non-zero positive integer. So this extended fields has symbols 2m minus 1, because we know that the n is equal to 2m minus 1, and this Galileo's field contains 2m minus 1 symbols. So in the Galileo's field, if we have 2 raised to power m uh, members, so it starts from 0 and ends up at 2m minus 1, right? So in fact, it has 2m plus 2 symbols. So here the two members are, one is the 0 value, One is the zero value, and one is the alpha naught, which is 1. And the other is alpha 2m minus 2. So this Galilean field is finite, having alpha is equal to 2m. So there are particular rules for addition in the Galilean field. First, we consider the polynomial alpha of x. So alpha of x polynomials have coefficients ai 0, ai 1, and ai m minus 1. So these are the coefficients which in fact belongs to the Galilean field polynomial that have a degree of m minus 1. If we have to perform the addition, we perform the modulo to sum between the corresponding powers of the polynomials. So the same way we do in binary cyclic codes. So the addition process is the same. Now let's check what will be the case. So if we have 2 raised to power 3 or m is equal to 3, so we have started from 0 to a7. But in fact, we are generated these symbols with the help of this generator polynomial. With the help of this polynomial, we generate this symbol set. So we consider this linear feedback shift register to generate the symbols of the Galilean field. This is in fact is a primitive polynomial which is used to generate this Galilean field symbols. So in that case, we start with the value of 1, 0, and 0. We will not start with the value of 0, 0, 0 because it is in a cyclic manner and it will remain 0, 0, 0. So we started from the value of alpha naught because the alpha naught is in fact is the equal to 1 and is the first symbol from where we start. And with the cyclic shift, we will able to generate the other symbols of the Galilean field. So what is the primitive polynomial and how we take the value of f of x, or we draw this linear feedback register with f of x. So in cyclic codes, we learn that f of x is a primitive polynomial, and primitive polynomial is irreducible polynomial f of x of degree m in way that n is equal to 2m minus 1. So in our case, we have choose the value of m is equal to 3. Here we take the value of m is equal to 3. that every symbol is represented by 3 bits. So the value of this polynomial is m in such a way that we can have n is equal to 2m minus 1. So the value of n is 7 here, and the f of x is of degree m, right? So this is the list of primitive polynomials with the corresponding values of m. So for 3, we have taken the value of f of x is 1 plus x3. So from this polynomial, we draw the structure of linear feedback shift registers, and from these linear feedback shift registers, we generate this symbol of the extended Galile's field. So this is, we know the rule for addition of the Galile's field. And what about the multiplication? How we perform the multiplication among the Galile's field? So for this, we know that f of x is 1 plus x3 is a primitive polynomial which help us to generate the Galile's field. So we suppose that alpha is the root of the polynomial. If alpha is the root of the polynomial, then f of alpha must be 0. So we can assume that 1 plus alpha 3 will be 0, and alpha 3 is equal to minus 1 minus alpha, because we are considering the binary field. So plus 1 is equal to minus 1, and we take alpha 3 is equal to 1 plus alpha. So what will be the value of alpha 4? So alpha 4 is alpha into alpha 3, and we put the value of alpha 3 here, that is 1 plus alpha, and that is equal to alpha plus alpha square. And alpha 5, we take alpha into alpha 4, and alpha 4 is alpha plus alpha square, and that is equal to alpha square plus alpha 3. Here we substitute the value of alpha 3, which is 1 plus alpha, so that will become 1 plus alpha square. And similarly, for alpha 6, we substitute the value of alpha 5, and we take this value of alpha plus alpha square plus alpha 3. And we know that alpha 3 is equal to 1 plus alpha, and alpha cancels alpha, and we get 1 plus alpha square. For alpha 7, we substitute the value of alpha 6, and that is equal to alpha plus alpha 3, and that is equal to 1, because V alpha 3 is equal to 1 plus alpha. So we substitute here 1 plus alpha, so alpha cancels alpha, and we get 1. So that is equal to alpha naught. So you know that alpha 7 is equal to alpha naught, and V goes up to alpha 6 in the Galile's field. So here, if you go back, you can check here that alpha naught is 1, 0, 0, and alpha 7 is also equal to 1, 0, 0. So after this, alpha 6, we will start repeating the symbols. So if we have alpha 8, so that is equal to alpha 1. And if we have alpha 9, that is equal to alpha 2. Because we have the linear feedback shift register, which repeats the symbols after alpha 7. Alpha 7 is alpha naught, and similarly the higher values will be mapped with this Gauss field symbols. So we have members that is equal to 0, that is equal to 1, and that is alpha 1, alpha 2, and we goes up to alpha 6 in this Gauss field. So here we have in our field, we have 0, alpha naught, alpha 1, alpha 2, alpha 3, up to alpha 6. So that is the 8 finite field members in this Gauss field. So let's goes on with the addition and multiplication rule. So we have the operation, a multiplication operation and the addition operation is represented by here. For example, if we sum up the same values, so we will get the zero answer, and you will check this diagonally. If we have the summing of the same values, we have the same answer. And alpha naught plus alpha is means that 1 plus alpha addition is give you alpha 3. You have seen this in the previous lecture, previous slide. So alpha naught plus alpha naught plus alpha is equal to alpha 3. So we have this value is equal to alpha 6, and 1 plus alpha 2 is equal to alpha 6. You can also see it from here that 1 plus alpha square, that 1 plus alpha square means that alpha naught plus alpha square is equal to alpha 6. Similarly, we map the entire table for this addition, and for multiplication we add up the corresponding powers, and if the power is 7 or greater than 7, so we consider it a 0 for a7, and a8 a1, a9 is equal to a2, and a10 is equal to a3, and similarly we have this multiplication table for the multiplication process. Because this addition and multiplication is used in the RS encoder. So for a simple test of primitive polynomial, that one test is that n is equal to 2m minus 1. So previously we learned only one rule for primitive polynomial, which is 2m minus 1, and the second rule we learned is that it is irreducible. So now we have the roots of this polynomial. At least one root must be a primitive element. For non-binary case, we have to remember that at least one root of the primitive polynomial must be a primitive element. So primitive element, when raised to higher order exponents, will yield a non-zero element, or that element contains in the field, or the field also the field is finite with the finite number of elements. So now we learn the RS encoding. So for RS codes, we learn that they have the property n minus k is equal to 2t, and the value of n is equal to 2m minus 1. And that code will be able to correct t errors and able to observe the location of t errors. So it means that if we consider a RS code of 7.3 and n is 7 and k is 4, so n minus k is 4. So it means it can correct two errors and find the location of two errors. So the generator polynomial is of the order of 2t, and the roots of this polynomial is alpha, alpha 2 up to alpha 2t, and in our case it goes to 2t is equal to 4. 2t is equal to 4. It means that if we have 4 roots, so one is alpha, one is alpha square, one is alpha cube, and other is alpha 4. When we have the generator polynomial with 4 roots, it means that x minus alpha multiplied by x minus alpha 2 multiplied by x minus alpha 3 multiplied by x minus alpha 4 will give the value of this generator polynomial. And that value of generator polynomial we have derived is alpha 3, alpha 1x, alpha naught x square, alpha 3x cube plus x4. And you can see that the power of this is equal to 2t, which is 4. So, so here we learn that the generator polynomial has 4 roots, and that number of roots is equal to 2t, and the power of this generator polynomial is also 2t. Now we have encoding a polynomial in a systematic form. So that's the same we done with the cyclic code, that we have the quotient and the remainder. Remainder is the parity which added up to the symbol, and that is the generator polynomial. So we multiply the message with xn minus km of x, and we divide it by the generator polynomial, and we get the quotient and the remainder. And by summing the remainder, we will able to encode the symbol. So this is in fact is the coded message symbol once we add the parity. And when we divide it by the generator polynomial after adding the parity, so the answer must be 0. So if answer is 0 after dividing generator polynomial, then we can say that we have a right code word. So we have u of x is p of x plus xn minus k m of x. Now we consider the example of the same RS73 code which we have considered previously. So first we have 3 symbols to encode alpha 1, alpha 3, alpha 5. So we write in the message in the form of polynomial, which is alpha 1, alpha 3x plus alpha 5 x square. and xn minus k is equal to x4. So we multiply this message with xn minus k. So we get the shifted version of the message, which is x4, x5, x6 with the same coefficient values. Now the generator polynomial, which we have calculated, this generator polynomial, we have four roots, and that is alpha, alpha square, alpha 3, and alpha 4. And we have generated this generator polynomial for this RS code 7.3. Now the parity is that we divide this message, shifted version of the message, with this generator polynomial, and we get the parity. And when we add this parity into the shifted version of the message, so we get the code word. So this is in fact is the right code word generated by the shifted version of the message and addition of the parity. So that is in fact can be written in binary form, that every symbol is representing 3 bits from this table, just like alpha naught is 100 and here alpha naught is 100, and similarly we have the code word in binary form. So this is in fact is the RS encoder. Now, actually, we have to learn that how we calculate the syndrome and how we correct the errors in the code word if it occurs due to the channel. So first thing we learned that 7.3 RS code has n minus k value is equal to 4. So it is able to correct only 2 errors and to find the location of 2 errors. So we consume that this in fact as RS code is encoded in the same way we use the linear feedback shift registers in the form of binary case. But here we have the symbols and we have to use the addition and multiplication table for this. For example, first we initially we have the contents 000 with the shift registers, and we fed back alpha 5 to the register. So we fed alpha 5 to the register, and when 0 is summed up, so it will not make any changes to alpha 5. So we have all value equal to alpha 5. So all these values are alpha 5. And this alpha 5 is multiplied by alpha 3. So alpha 1, alpha naught, alpha 3. So what we will get when it multiply by that is alpha 1, right? And that is in fact alpha 5 when multiplied by, we get alpha 6, right? And here we get alpha 5 multiply by alpha naught, we get alpha 5, and here we get alpha 3 multiplied by alpha 5, we will get alpha 8, which is alpha 1. So here the alpha 6 is when sum up with alpha 0, we will get alpha 6 here. So 0 will add up in these values, will not make any further change. So we have here alpha 1, alpha 6, alpha 5, alpha 1. Next we have the feedback with the alpha 3. So alpha 3 when multiplied by when sum up with alpha 1 will give you alpha naught. So the feedback is alpha naught. So in short, finally, when we have three messages input, so we will get the value of the shift register alpha naught, alpha 2, alpha 4, alpha 6, and these k values, first four values, and then the last three values. So here you get first n minus k values, and then you will get x3, and this will be the last three values. So this is the hardware architecture, and now we learn about the error correction of this encoded systematic code word. So for first rule we learn is that we know that this generator polynomial has four roots: alpha, alpha square, alpha 3, and alpha 4. So the roots of the generator polynomial will also be the root of the code word. So u of alpha square, u of alpha 3, u of alpha 4 is also 0. So the roots of the generator polynomial will also be the root of the code word. So verify that our code word is correct. So we put the values of the roots and we generate the answer. If answer is 0, then it is a right code. Now, in decoding, we assume that we have a particular error pattern. So we assume the error pattern is of two symbols, because we cannot choose an error pattern which has more than two errors, because it is a 7-3 code and n minus k is equal to 4. So it is able to correct two symbol errors. So all the error patterns we can assume is of two symbol errors. So that error pattern is of two symbols. So at the location x3 and at the location x4. So first we need to find the correct value of this in the code word, and we need to find the location of this. So this is in fact is unlike with the linear codes, where we have the binary version and we can easily calculate the error patterns, and then we calculate the error pattern, and then we find the syndromes, and from these syndromes uh, we just try, we have the lookup table to find the errors, find the correct code words. So here we see that we have two errors in these two symbols. 4 bits are in errors and 3 bits 3 bits corrupt one symbol and 1 bit corrupt another symbol. So the received word is in fact is, this is the received vector. Now to check that received vector is equal to u of x. So if the roots give us the 0 result, then it means that is the correct code word. If the roots give us the wrong result, non-zero values, So it means they have some errors. So, uh, so first we calculate the syndrome on the basis of the roots. So if the roots are alpha I, the range is from 1 to n minus k or 2t, uh, we have the we have calculated the syndrome in it. So the value of the syndrome vector is in fact is also we have the syndrome vector from 1 to n minus k. So this syndrome is also of n minus k uh, patterns. So we have these the value of these syndromes are given here, and that is S1, S2, S3, and S4. That is calculated by substituting the first root, second root in the receive vector, third root in the receive vector, and the fourth root, which is the n minus kth root of the vector. Now, for error location, we assume that there are V errors, and these V errors are located at uh, J1 location, J2 location, and JV location. So this is V errors occurs at the J location, uh, and we have to calculate the location of this vectors. So first we have to find the error polynomial. So error polynomial is in fact is written in this form, ej1 xj1 or up to ejv xjv. So this can be written in this form because this error is in fact is the non-zero value, and that location is that their locations are is in fact are the uh, beta L. That location is beta L, and that is represented in the form of alpha. That can be represented in the form of alpha. So we can write the syndrome in the form of error patterns. So we can write the syndrome in the form of these error patterns. So the location is here for alpha square, we have the beta square location. And for alpha, we have the alpha location. And for alpha 2t, we have the 2t location of the beta. So it forms a matrix, and from this matrix, we can generalize the uh, uh, roots of this sigma of x error located polynomial is 1 by beta 1, 1 by beta 2, and 1 by beta b. And that error located polynomial is written in this form. So this will in fact is 1 plus sigma 1 x, 1 plus sigma 2 x square, and 1 plus sigma v xv. So we write this in that form that we start from S1 to ST, and we ends up with ST to S2T minus 1. And we start with error location sigma t, and we stops here at location sigma 1, right? So this is in fact is the syndrome matrix which help us to locate the error polynomial, and once we locate the location of the error polynomial, then we will try to find the values of these polynomials. So here in our case, we have two errors, and we have syndrome S1, S2 and S2, S3, and here that would be equal to S3, S4 syndrome values. So because that is ST minus 1, and here we start from ST to ST plus 1. So we have calculated the value of the syndromes here. So here the S1 value is alpha 3, S2 value is alpha 5, S3 value is alpha 6, and S4 value is 0. So we calculate these syndromes and we put up these values here. Put up these values here. And from this, we calculate the value of alpha sigma of sigma 1 and sigma 2, and we will put these values in this equation, which is error locator polynomial, and that error locator polynomial is alpha naught sigma 1x sigma 2 x square, and we have find location of these errors with the help of this locator polynomial. Now the location, for the location, we substitute the value of the roots in the error polynomial. So first we substitute alpha naught to alpha 6. So if the value is non-zero, so it means there is no errors. So where the value is 0, so we mean there is an error. So the location of this is in fact 1 by beta 1, which is alpha 3, and 1 by beta 2, which is alpha 4. Vice versa, we can say that beta 1 is equal to 1 over alpha 3, and beta 2 is equal to 1 by alpha 4. So to calculate the value of A alpha minus 3, we check all the values of alpha 3 in multiplication table and find where it is equal to alpha naught. Where the value of alpha 3 is alpha naught, we choose this value, that is alpha 4, and that is alpha 3. So the location is, so the J1 location is in fact is error 1 alpha 3, error 2 alpha 4. So it is x3 and it is x4. So the location of error is x3 and x4. So half of the work is done here. If you check in here that the error is at x3 and x4 here. So now we have to calculate the values to calculate the values of this. We have take the syndrome 1, which is E1 beta 1, E2 beta 2, and E1 beta 1 square and E2 beta 2 square. So we equate it with the syndrome S1 and S2, and beta 1, we will take the value of beta 1 and beta 2, and we have the squared value of this. And from this, we calculate the E1 and E2. And the value of this E1 and E2 will be A2, A5. So the error value is, in fact, the error pattern is we have here is that is equal to alpha 2, and that value is equal to alpha 5, and that value is at the location of x3 and at the location of x4. And in the receive vector, if we sum up the error pattern, so we have the correct code. So we get the correct code word. That is the 7 by 3 RS codes, and we have completed the part of RS code. In the next lecture, we learned about turbo codes. Thank you very much.